unfortunately, what I have to tell you about is a mystery, this big, mysterious, cool, weird thing that's, in fact, not cool and not mysterious. That's what happened. So that's the story I have to tell you about today. The weird thing that turned out to be not weird at all, and yet it was published last July in Nature. I've been fighting ever since to get the right explanation out. So this really isn't my research per se, it's just what we do in foundations. You get these experiments, and then everyone has, I have an interpretation of quantum I developed from, and it started about 2004. It took me 10 years before I found my own interpretation, and then the past 10, 11 years I've been developing it. And what you do when you have an interpretation of quantum is, you just look at the experiments, the weird experiments, and then you say, oh, here's how we explain it, and everybody brings their interpretation. So, well, here's how we explain it, here's how we explain it. Okay, so for example, here's one that I like to show people because you don't have to do any statistics, you don't have to do any quantum. I can show this to visiting people that visit our college, visitor day, people that don't even know anything about quantum and say, this is the kind of thing that's weird about quantum. So, you have a pair of photons, an experiment that was done by Zeilinger. It was published in 2004. And you have a pair of photons emitted here at the same time. They're entangled. Entangled means what you do to one bears on the outcome of what you're going to measure with the other guy. So they come out of here, go in from the same spot, the same speed, same place, boom. And then this guy goes to the computer, and then when this guy hits this detector, which is either here or here, depending on where the experimentalist wants to put it, that tells you where to put, which bin to put this guy in. Okay? So if this guy hits here, you put this guy into this bin, and when the other guy hits here, you put this guy into this bin, and you see these two nice patterns come out. Okay? Again, you don't have to know, if you know quantum, you know this is wave particle duality, and if you know optics, you can see this is 2f, 2f, focal length, and blah, blah, blah. But just from the weirdness perspective, you realize, wait a minute, how can this be? Because you said, the pattern this guy makes, this or this, depends on whether his buddy was detected here or here. Is that right? And absolutely, that's true. Well then how can if he hits here and his buddy's here? How does his buddy know where that detector is going to be? And in fact, in these quantum experiments, you can be moving this thing fast enough so that there's no way that this could be done, right? Now in this particular experiment, I don't think that was the case. But when they do the Bell entangled states, they have megahertz frequency changes in the polarization angles. So, again, the quantum doesn't care about free will. Didn't I have free will to move this and put it where I want? No, because if he went in here and decided to be this, you don't have any choice. You're going to have to put his partner here. After he already decided to be this, right?
The two curves, one of them, presumably, one of them's interference and one of them's not interference.
Right. Yeah, that's what if you send particles to a pair of slits, you'll just get two hump images of each slit, and you add those together, and you just see them in one hump. But if you send waves through a pair of slits, you get an interference pattern. That's wave particle duality. But the weirdness is what's called delayed choice, right? How does he know what I'm going to do? So Merman says about these things, and I show this to my students when I teach intro to quantum. Shut up and calculate. David Merman said, I was always told, when I started to ask questions, how can that be? He was told, just shut up and calculate. Quantum says this, we observe this, don't ask questions.
But the explanation, I mean, there's lots and lots of speculation and sort of like you said, but the one thing I never see in any of these is Feynman's approach with the many paths interpretation is, you just sum up all the possible paths, and of course, if it gets to this point at this time, then it's cut off a certain number of paths, and the interference of all the different amplitudes to get there, it explains things perfectly.
You'd think you would at least have like a distribution around it, right? No, if it makes the one pattern, then this buddy is always in that spot, period. No, there isn't any.
Yeah, but it has to be. I mean, Feynman's, you go all the possible paths, and
yeah,
you
in fact,
close some
my interpretation uses relational. It's called relational block world and depends on the path integral formalism. Because in the path integral formalism, it's an extrema, least actions. So, you talk about, you put the end state in. You say this outcome. So if you're in space-time picture, that's fine. All right? You can talk about what's the probability given a spatio-temporal configuration. Then you're not talking about things moving in space. carrying intrinsic properties, then there's no problem. And in fact, that's the basis of my interpretation. But I'm not going to tell you about that today. I'm just going to show you about this simple failed thing. So here's what you do. So you get those experiments, you bring your interpretation to bear on it. And so here's one that came out in 2013. That was interesting to me because this is called so-called weak values. And I didn't do anything with weak values. I hadn't seen any of their weak values experiments. So this is one that they say, here's this weak values experiment that's easy to understand, and I want to go through and bring my interpretation to bear on it. This is an interferometer inside an interferometer, nested interferometer. And they jiggle these mirrors, these 5 mirrors in the interferometer, very small amplitude so as not to affect the overall interference patterns, and you get destructive interference out of here and out of here. And then you see, associated with the vibratory frequencies of each of the 5 mirrors, you see these peaks, then in the signal at D, okay? So now, what they do is they adjust this distance between this mirror and this beam splitter, so now you have destructive interference here. So now you have constructive here and here, and you see the beam only comes here from mirror C, right? And you think, well, what am I going to see here now? Well, what if I block this beam? What do I see? Nothing. Okay, well, dude, there's nothing getting to the detector if I block this beam. The information about these mirrors is going down here. There's nothing available about F. There's no beam hitting him at all. And anything coming from C got blocked, so I don't see anything. Yeah, that makes sense. Well, what about here? What would you think? And Weidman, who did this experiment, in his presentations, he'll sit and wait for the audience to guess. I'm not going to torment you. Here's what you see in this case. So that's kind of weird. You're thinking, well, wait a minute. Why are there signals from mirrors A and B in here? And if information about A and B is somehow getting to detector D, then why isn't information about E or F getting there? You know, what's going on, right? Now, you can explain this to first order with ordinary quantum and to first order approximation. Of course, quantum optics takes QED, solving Dirac equations, stuff like that. But you can also explain this with what's called photon leakage in classical E&M. And then what you understand to be the case is, what's going on is, there are photons from E and F getting here. They're just in the background. You can't pull them above the noise of the background, that's all. Because you're going to have destructive interference. Between the source and the detector and E and F, you're going to trace these paths. But this guy down doesn't interfere with this guy down. When you do the wave equations from E and M and do it out, you'll see. But this let me understand what weak values is about. There's weird stuff because the stuff that's just like, it's just too small to be seen. Okay, so that gave me sort of an intuitive understanding of what these weak values are all about. We included this in the paper that we published in June. This was being done last summer. It takes a while to write the paper and publish it. All that junk. So we have this experiment explained per relational block world, and in the meantime, this experiment came out in Nature Cop. Quantum Cheshire Cat, and this is what I wanted to talk to you about. Okay, so this got published, and you see their claim is they have a neutron interferometer. They send neutrons in here, and they said at the end I'm going to detect my detector here. What I get here is going to give me evidence of the fact that neutrons that end up at this detector took this path, while some property of those neutrons took the other path to get here. Okay, we're going to do something like that. Okay? Now, this is immediately, I was like, what does that even mean? To say, Joe Hemsky is here, but his height is over there. So I was immediately intrigued. I want to see what they did in this experiment, figure it out, and then I'll include an explanation for relational block world, in our next paper. Okay? So this is their own diagrams from the paper. So here's what they did to ascertain where the cat is. What they did here is they turned the... Oh, this may be a better diagram. That's a pretty picture, but I like this one better. They take the neutrons that come in here, these two paths, and they give these guys state spin x up, or negative, down, sorry. And these are x plus, okay? And you can follow along even if you don't really totally understand what spin is. I'm going to tell you what the effect of the magnetic field does on this property. You know, so if you don't understand spin, you haven't seen it yet in class, don't worry, it doesn't matter. So there's this property, okay? It's x plus that they gave the neutrons in this path, and x minus that they gave the neutrons here. And then you go through this last beam splitter, and they select out here the minus guys, and that's where their detector is after that, okay? That's what they do. So when they put a weak absorber in this bottom path, that's where the plus guys are. So you attenuate the signal with respect to the plus guys, but you're only looking for the minus guys, and so you don't see anything at your detector. So you select out just for minus guys. So you attenuated a few of the plus guys, but who cares? You're not looking for them, right? When you put it up here, then you've attenuated, you've gotten rid of, absorbed some of the minus guys, and that's what you're looking for, and so sure enough, your signal decreases a little bit, okay? That's the cat. So then they say, look, the neutrons that are reaching this detector took this path. Well, in that part of the experiment, yeah, that's true. Okay. And there's nothing about that part of the experiment that's of further interest or mystery or anything else. It's the property part where things get ugly and go awry. Okay? So, what about this spin property? Well, it's not the x property that they're going to explore. It's the z spin that they're going to explore. And they're going to do that by introducing a weak magnetic field in the z direction to each of the two paths in turn and see what the effect is at the detector, okay? So, we would expect, we're going to put it here, if we want the grin to make a claim at the end of the day that the grin, that this z component of spin was on this path, then when we stick the magnetic field dz on this path, that's where we expect to see a difference in the signal. And in fact, they see an increase. They see a slight increase of 3% when they put the BZ on that path. Slight increase in the intensity, 3%, which is above, that's above the uncertainty. I think it's like 5 sigma out.
Are you switching the axes, or do you see a change in the x component when they put BZ on?
Yes. Oh, I'm sorry. For those of you who know quantum, you remember sigma z takes sigma x and flips sigma x negative, and sigma z flips it to a minus, a plus, switches a plus to a minus. Well, I'll say that in a minute. Right now, I'm just going over qualitatively what they stuck where, what they saw, right? We're just sticking to that right now. So that's good, right? That's in that. They stuck the magnetic field here, and they see an effect here. Okay. You know, at the end of the day, you may or may not buy into this ontology, but at least that's consistent with the picture. The next part is what kills it. You stick the magnetic field here, that's not supposed to be there, right? But in fact, you see a 3% reduction in the intensity, which is exactly the same size as the increase you got from sticking it here. So immediately you're like, uh-oh. I mean, if I want this picture, doesn't this have to be nothing, right? Don't I need like this? Absorber? Yes. Absorber? No. BZ? Yes. BZ? No. Isn't that sort of what I need? But they got BZ? Yes and yes. By the same size difference. Oh. So I was like, dude, how is this? Right? What's going on? What's going on?
I don't understand the interaction in the Hamiltonian is mu dot b. So if mu is in the x direction.
E to the I, sigma z, theta is the interaction with theta is your interaction strength. That's their interaction operator. With a projection put in for E weather
interaction is not mu dot b?
No. Sigma z theta is the interaction.
What's the
Sigma z, the Pauli Z component.
sigma z is, but what's theta?
Oh, that's the interaction strength. They probably did a mu dot b and then replaced it with sigma z theta with theta as the strength of the interaction.
Yeah, but mu dot b would be 0, because mu is in the x direction and b is in the z.
Oh no, dude, you're not going to get a 0 interaction between a bz and a, it's going to flip it. There's a definite interaction. You see it right here.
It's just precession.
Yeah, dude, of course. Okay, so
Like you have a fixed magnetic moment.
what makes them take this picture and in any way, shape, or form try to justify this ontology? Okay, well, the way they do it is by what they call weak values. All right, weak values are, and I'm not going to go through any weak value calculations. I'll show you in the next slide how they're defined. But the weak values that they find appropriate for their outcomes that they measured in this experiment are these right here, these 4 weak values, okay? I'll explain how they related to the outcomes and stuff in a minute, and I wrote them down here because we'll have to refer to them more frequently. But you have a projection operator on path 2 is 1, but the projector operator on 1 is 0. So this is path 2, path 1, and so they say, well, this corresponds to where I put the absorber. When I put the absorber on path 1, I had no effect. When I put the absorber on path 2, that's where I got an effect. When I put sigma z, when I put the BZ field on path 1, I got an effect, but when I put the BZ field on path 2, well, I'm not supposed to get an effect, right? But I did. Oops. But nonetheless, these are the weak values that go to explain the outcomes they actually measured. So now I'm like, wait a minute. How do these correspond to these intensity variations? So I'm going to go through this thing myself. I'm going to derive my own intensities, do the first non-vanishing order expansions to the strength of the interaction parameter, etc. Get my own intensities, match them to the experimental outcomes, and see what's going on without all this weak value stuff, right? Okay. But this is the whole key to the thing. Those 4 weak values actually do obtain for this experiment. Okay? That is true. They just don't, at the end, mean what, obviously, they need them to mean. Okay? And that's the punchline. So here's how weak values are defined. I never studied weak values. I didn't follow their calculations through to the derivation of the intensity that I'm going to show you in a minute because I did my own. And my own in the first order expansion maps right onto there. So I said, all right, however they claim to have done it, clearly it's correct. So I'll let them, that's their area, whatever they say. So here's the story. You take an operator, and this defines the weak value of that operator. And for this case, this is your initial and final states. They call it pre and post selection. I'm sorry, I'm not exactly sure. I went through a couple of their experiments now, and what they consider pre and post selection seems to be somewhat arbitrary, but nonetheless, if you define these states like this, and this is how you define the weak value of an operator, you will get a nice picture for the intensity to first order in terms of the weak values. That's true, apparently, and it's fine, and it works fine too, so we'll just give them that, right? Okay. So now, I'm going to go through this myself and explain what the hell's going on, okay? Not in terms of weak values, but just in terms of quantum mechanics. So here's the story. If you obtain the intensity when you have the magnetic field in path 2, that's up here, then you get this, and this is your, I said theta, I'm sorry, it's alpha. You get that, and they have this equation in their paper too, that's good. You take their values, their reference intensity before they do anything, and then after they stick it in, they got here. And these are the plus or minuses there. And they have this alpha is 20 degrees, plug it in, it works. It gives you exactly what they observed. Do an expansion of this, and you get this functional form. And this order, within these uncertainties, this works to give you the answer, right? Okay. I got that much, I see that. 3% reduction, okay? And let me just go ahead and say what I said before. I hadn't intended on throwing in this part, but what's going on is BZ takes sigma x minus and turns it into sigma x plus. That's what it does. If you do sigma z on the x minus state, it's minus x plus state. And sigma z on the x plus gives you a minus x minus state. So it's just flipping them. Not all of them, because it's weak, but it flips some of them, and that's what's happening. It's flipping some of them. So when you put it here, you're only looking for the x minuses, but you're turning some of them guys into pluses, and you're not looking at, you're not seeing them. When you stick it here, you're turning some of the pluses into minuses, adding them to the minuses you already have, and so you expect you're going to see, an increase, and you do. And you do. Now, whether or not they're the exact same size, let's do the calculation and see. So this is the intensity that you get for your neutron count at the detector if you put the magnetic field in path 1. And again, the numbers with alpha equal 20 degrees, and take their reference count, and you get their value that they got within, and they overlap within a sigma each. And you can get that agreement if you just look at the first order expansion. It's fine. So this is sufficient. Alpha is small enough, it's weak enough, the interaction is weak enough, that this approximation to the full-fledged intensity equation works to give these numbers within experimental uncertainty. Okay? So, I guess that's weak values, right? It's weak, it's a weak thing, and it makes sense. And so, let's see there. Let's see what they're saying. Here's their equation. I remember I told you they have an equation for the intensity using the weak values. And now this is only valid. They chopped off the other piece of the full-fledged intensity. They're only keeping these first two orders, right? In terms of the interaction strength alpha. And there's alpha squared. In fact, this is what they use when they claim to have measured their weak values. Well, of course, you say, well, they didn't measure the weak values. They got a weak enough BZ that it works. I mean, if it didn't work, then they just don't have a weak enough BZ, or they screwed up their calculation. I mean, it's not really a measurement. But that's my bias. And apparently some of my papers, when I put scare quotes on the measure, some of the referees thought that was a little polemic, so I toned it down in my last submission. But anyway, here's the story. So look at this equation. So this is your reference intensity from the previous. So look at this. If you want this to be, let's say 1, J equals 1, that's path 1. And J is 1. Then this guy is 0 here. And this guy is 1. I had to put plus or minus. When I did my calculation, I got a -1. But it doesn't matter, it's squared, but I hated to put +1. When I calculated, I got -1, so I hinted that I got something different myself. But anyway, this gives you this guy here. And then when you do path 2, 2, he's there, and 2, he's not, and that's this guy. And that's exactly these two equations that I just got, with the first order expansion. So their thing works perfectly well with their weak values, and this equation gives what I know to be the correct quantum physics and works with the experiment. It's a very nice quantum experiment, okay. But now you see what the problem is. Remember at the beginning they said this weak value is associated with the absorber. No, this weak value is in fact associated with the BZ in this path. And in fact, when you go through the calculation, you realize immediately what that projection operator is telling you. It's telling you, dude, if you stick anything in here that changes the minuses in any way, you're going to see it here. That's all it's telling you. There's nothing else mystical about that. The sigma z is changing in a way that's not going to be detected here. We don't care. Okay? So, let's go through and see where did they come up with this idea, right? That these things mean what they mean. By the way, talk's almost done. I got like 2 slides left. This is the very end, just when we pull it all together and see where I'm saying they made a mistake. Okay? And it's not with the experiment. The experiment was done beautifully. It was with the fact that these weak values don't in and of themselves imply the situation. There's another qualifier that has to be added, and that's what we have to see here. So here's the story. Here's your interaction operator, right here. I sigma z alpha over 2. And here's its expansion to first order. Okay? Now, if this is the expansion, the operator first order, and so you're saying, I'm going to make alpha weak enough that the quadratic and higher terms don't count, right? Okay. Well, if I take that and I stick it here, this guy isn't going to change the pluses, so it doesn't matter. This guy's going to turn some of the minuses into pluses, so that's going to matter. So that isn't that my sigma z projection 2? No, I don't have written. E is 1. And in fact, that does matter, and that's good to go. If I stick this guy up here, this guy turns some of the minuses into pluses, but I'm not looking for pluses, so that doesn't make any difference. This guy just hits the minuses and keeps them the same. So then to first order, to that order, at least I should get the same thing here. Okay? So that would be your sigma z2 is 0, and that entails that you have no effect here. But we didn't see that. We see something here. And it makes sense that we see something there too. I mean, intuitively, right? I mean, what the hell is going on? By the way, it took them weeks to get me to this point. Yeah, 46 pages of email exchanges with the authors of the paper. NatureCom, you don't write a comment. You go to the authors first. Hash it out with them. Then go back to NatureCom with all the email correspondence, send to them and say, here's what they say, here's what we say. Can you write one, you only get one page, 600 words, rebuttal to whatever claim they made. And so that's where it went. So anyway, they had to lead me through this because I don't know anything about weak values. You know, I did my analysis and said, what? You know, I said, what the hell did you do? And they said, oh, this is weak values. You have to know about weak values to understand this. All right, well, did this calculation like this? And they said, no, you have to do that. And then like this? Well, you got to look at it like this. And then finally, I figured all this out. And then one of the theorists on the project said, well, you're right, we can't do it with this experiment. It can't be done for the reason that you finally dug through and figured out. But, you know, just let it go, you know. And I said, dude, why would you publish this claim when you know it's false? I'm going to submit the VCA anyway. And he said, well, good luck getting anyone to listen to you. So, and he's been right. It's been a funny story, I'll tell you at the end. So you go through these weak values here, and they map on. That's what I just said. Here's what's going on. So what if we, instead of just keeping the first order term, what if we keep the quadratic term? Title of the talk, quadratic interaction in the. What if we keep the quadratic term? What do we get then? All right, well, pair that up here. The identity piece, right? So the complex piece is the linear term. The 0th order and 2nd order terms here go with the real part of the operator. And now it works. This works beautifully to tell you what's going on here. Because now you get that decrement, see? This is the decrement you get, the alpha squared decrement, is what you get up here that you don't want. So he's the bad guy. He's the bad guy. He's the guy you need to get rid of. It's what the theorist said. We know the effects there. You just, in this particular experiment, you just can't get rid of that guy. Why can't you get rid of that guy? And now, when I teach this spring, I'm going to teach quantum again, and I'm going to put this in because it's just a classic undergrad quantum calculation to get all this stuff. And I would ask my students at this point, so why the hell can't I get rid of him? He's alpha squared and he's only alpha. Isn't there any way I can make alpha weak enough to make this negligible? And the quantum people would immediately tell you they know. Right? You guys know quantum, you're like, yes, of course, you square. Observables are not amplitudes. This is the effect on the amplitude. To get what's observable, the intensity, you have to square it. And when you square this complex guy, there's your alpha squared, and this squared is going to give you a cross term that says alpha squared, and exactly what you see. You can't get rid of this. You can't get rid of this piece. And it sort of makes sense that you can't, because look, dude, if you're flipping some of these guys and not reaching here anymore, you think in exactly the same amount, right, the same intensity that you're turning these guys on, you're turning these off, come on, you're not going to see this, but you see this? I mean, intuitively, you think that doesn't even make sense. And quantum says, settle down, Stuckey. Quantum makes sense. It works. Observationally speaking, you can't get rid of this guy. So that's finally the whole, now I get it. This plus linear interaction. If you have an experiment where the quadratic terms are higher, contribute to the construct of these, then who knows? All bets are off. We don't know what you're going to be able to infer. But if you have linear, then it would work. And that's the conclusion.
I don't think your argument's even more, go back to.
Oh, I'm sorry. That's it, by the way. I'm done. The talk's over.
I mean,
So now you can ask questions.
the argument about the error of what they did is more compelling, just to take the e to the I sigma z alpha, and instead of expanding it, it's, you know what it is exactly.
Yeah, it's easy to see, isn't it? It's a beautiful quantum experiment with a very simple introductory quantum level analysis, gives you all the results. My question is then at the end, they see all that. They had the right equation. They saw that you need a projection operator to account for this effect, right? And yet they say the projection operator only goes with the absorber. When you see from your own equation, your own data, you need it for this guy, right? Why are they saying that? Why did they?
It seems like they hoodwinked themselves by expanding it and saying it's going to be weak and we're only going to keep the linear term.
Well, then why did they end up with this? How did they end up with this equation where this has to be taken into account for the magnetic field? Why is this in there at all, according to their view, right?
No, but I'm just saying, if they'd solved it exactly in the first place and hadn't expanded out, that is into that. I mean, your expansion there.
Yes.
There's no reason to expand that and then throw away the other terms. You can
absolutely
solve it exactly for any field
absolutely
that you want, and you'll always get the right answer.
Yes, and it's perfect, and it maps on beautifully to the experimental result. So that is the question at the end of the day, right? Why the hell do they make this claim?
Well, not only that, but who refereed the paper for Nature or whatever?
Well, that's a big, long story. There's a lot of parts to it. Turns out when I was at a conference this summer, Weidman was there. He's buddies with a buddy of mine, Avi Elitzer. So he sat down with us and we were chatting. And I said, "What do you guys? You guys are in weak values now, right?" And Weidman, by the way, was the pumper guy. That was his experiment. So he's big into weak values. And I said, "What do you think about this Denkmeyer quantum Cheshire Cat thing? Did you analyze that? Because I analyzed that and it doesn't make sense. And I'm having trouble getting anybody to publish it." When I sent it to NatureCom said, "This is a new. You're making a technical claim. You're claiming this isn't sufficient. This has to be added to the list of criteria to make the inference." And so NatureCom said, that's got to go in the journal separate. That has to be refereed separately. So I went to the journal. I went to American Journal of Physics. I went to PhysRev A. I went to Foundations of Physics. They sent it out to referees. Referees all said, yeah, this analysis is trivial. Quantum mechanics, clearly Stuckey's analysis is correct, but we can't publish this paper. This is a comment on the paper in Nature. That's got to go back to Nature. So we took it back to Nature and said, 3 editors, 4 referees all said the same thing. The analysis is sound, but it's got to go in your journal because you published a paper. And they came back and said, no, this is a new technical result. It has to be published elsewhere and established elsewhere. It can't be.
But that's what I'm saying. Your argument is more compelling because their argument is wrong. It's not a new technical result. Their analysis in the first place was wrong because they expanded it out and they never should have expanded it out. If you just do the quantum mechanics and solve it exactly for weak values, strong values, any value you want, you get your answer. It's not a new technical result. Theirs was a wrong technical result in the first place.
Well, the implication for the whole weak values program, see, that's where I sort of agree with NatureCom in a sense that their whole program, see, is based on not just this experiment, but other experiments. You compute these weak values, and you're supposed to be able to make inferences about what's going on, right? And they mention this, but they never add it as this is necessary addendum to whatever the weak values are. So when I gave my talk in Dechau, I switched. I was going to talk in relational block world, but since all these weak values people were there, I said, dude, I'm going to give them my version of quantum Cheshire Cat. Well, it turns out Stephen Sponer, one of the experimentalists on this, he was presenting in my session right after me. I said, oh, this is awesome. Stephen, my name is Mark Stuckey, and nice to meet you. He said, yeah, I know who you are. He said, why are you giving our group such grief? And I said, well, I'm going to talk on that here, and you can correct anything I have to say if I got it wrong. So everything I showed you about the experiment, what they did, he sat right there and I kept turning to him. Is that right, Stephen? And then you put the magnetic field here, right? And you found a 3% increase, right? And then you put it here. Is that right? Yes. You found a 3% decrease in the intensity here. Is that right? Yes. And so at the end, I said, so Stephen, what? And he was like, just shaking his head. And he said, the theorists told us. He said, I'm an experimentalist. I don't know anything about the weak value stuff. But the theorists told us, if we measured these values, and they do, these are the values, the weak values that make this equation hold, right? And it does hold. And so we got it. We set it up. We got a weak enough situation that this would hold within experimental limits. So that is the set of weak values. And this is quantum Cheshire Cat. That defines it. That and that alone. And I said, well, Stephen, if that's true, you shouldn't have published, we did quantum Cheshire Cat. You should have said, we have a reductio against this interpretation of quantum Cheshire Cat. Because we did this experiment and got these values with this picture. And this picture is not this picture. So if you believe, I'm saying, Stephen, you should have said as an experimentalist, if you believe this is that, we did an experiment to show you that this is this, and therefore that does not always hold. We have a reductio against this interpretation. Instead, they published, oh, we did it. We are the first ones. This is what we got. We saw this. And he, after the talk, I told him the name of the theorist in his group that told me that, good luck getting anybody. You're right. And he said that I was against making this stronger claim, but I was outvoted.
But I reject the whole notion that equation is the right equation.
Oh, the whole point of this is simply, remember, it's weak values, right?
No, but that's my point. It doesn't matter what value. They should be able to, I'm sure, you can derive an equation that holds for any value whatsoever, whether it's weak or not.
Yeah, well, we have those.
And it won't be that equation.
No.
And
No,
so
the whole point of their program
interpretation is based on that equation.
Yeah, their whole program is simply that supposedly weird things happen when you look at the weak interaction regime. That's their whole program.
No,
I'm not here to defend it.
But I'm
So
saying that it doesn't, how can they even say that? You can
Well-
solve it exactly, and the exact answer holds for all the
Yes.
values. They can't get that equation except by expanding it improperly and throwing away all the values that matter.
This equation is correct. This is the correct equation of the first non-vanishing order and expansion. And they did make the field big enough that this was applicable. This works. This gives you the answers. That's not the problem at all. The problem isn't that this doesn't work. It works. This works. This maps right onto those. I don't have my two approximate things that map right onto the data. There's no reason to say that this is bad or wrong. The only thing to say about it is, what does it mean? See? Weak values is all about foundation. Foundation is all about, well, what does it mean? What's really going on, right? Well, they say, look, if you do weak enough interactions, get this to work, and then you'll measure these, and that means this. Isn't that weird? See, that's what they want. Unfortunately, in this experiment, this doesn't give that. It gives this, even though this is true.
I'll try it one more time and then I'll give up. If you start with e to the I sigma alpha over 2, and you use the exact form of that, which is a nice simple matrix, and we calculate this ij mag
intensity for the magnetic field.
And use the exact value.
Yeah, I had those.
You should get something different.
Oh no, you don't. Here it is, right here. Here are the first order expansions of the exact forms.
I don't want the first order expansions. I want
Oh no, but that's what they do want. That's their whole point. That something is there.
I don't know why this is so difficult. If you do it exactly,
yes,
and don't do a first order expansion,
then you're not doing weak values.
Yeah, you are. You can put any value in you want.
Yeah,
and it can be weak.
But then that equation doesn't hold.
Exactly. That's the point.
Then it's not weak values.
The equation's wrong.
No. This equation is correct to order alpha squared. And it works in this experiment.
If you put the exact equation in...
You don't have to use the exact equation. How much physics have you done where you didn't use the exact equation? At least half of all the physics we do isn't the exact equation. When you type pi into your calculator, it's not the exact answer.
It's always an approximation.
Right, everything. BE is approximation. So
if you do it exactly,
you do
it will be an
you do this.
approximation.
You only need to do it to the extent that you're comparing with the experiment, and this works. It works.
You just showed that it doesn't work.
No, 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 no. I never showed you that it
They were the
worked.
wrong.
This does work. What I showed was the weak values that make it work give this, not that. No, no, no. Computationally, I'm sorry if I misled you. Computationally, there's nothing wrong with this expression at all. There's nothing wrong with these weak values in that expression. They give you the thing. It all maps on the experiment. There's nothing wrong with that. The problem with it is, do these entail this? And the answer is no. In this experiment, these entail this. And this is not that. So they could have said, we did your weak values, done, there's your values. We didn't get that, we got this. Clearly your weak values don't mean that, unless you can do linear action. So we have a reductio. If your claim in the weak values community is, this alone entails that, then these experimentalists could say, we have a reductio against that interpretation. But they didn't publish that at all. Instead they said, we did this. What? So,
I have a different question here. I went on the internet to look at some of this stuff, and I saw that somebody was going to publish a paper where they used quantum interference to explain all this.
yeah, Paul,
Now,
Corey.
I don't know what quantum interference is,
Yeah.
deep down anyway. Is there,
Yeah,
how is that different
Wrong.
from what
Raul,
you just did?
Raul Correa published. He and I have been in correspondence since I wrote my first paper, and I had his paper. Yeah, he explained the original quantum Cheshire Cat experiment was done by Ronoff in New Journal of Physics. And he didn't do it with neutrons, he explained it with photons and was called a pointer state. And Raul came in his group and showed, you can show how that result is, again, assuming a linear interaction only, is just quantum interference to get that effect with the photons. That's true. And they don't deny that or anything else. Quantum interference in quantum mechanics is, that's what Feynman, he was talking about Feynman. Feynman said there's only one mystery in all of quantum, and that's quantum interference. So when Correa wanted to publish a paper saying Cheshire Cat can be understood as the mystery associated with quantum interference, they're like, so, okay, sure, quantum interference is mysterious. We just want to say this is weird. Isn't it weird? And maybe it comes from quantum interference, you can understand it that way or not. So, but his analysis for this experiment doesn't work. Because he said there's no pointer state. He wouldn't even know how to begin using his analysis. But he saw my paper and said, boom, and you got it, you nailed it. He said, that's exactly right. This is exactly. And then another guy who works with the Ronoff is the guy who published this paper about the photons in New Journal of Physics, who asked not to be identified as well, said, he looked at this and my analysis and said, yeah. And in fact, he published a paper with the Ronoff in January. This paper came out in July last year. This January, they published a paper talking in part about quantum Cheshire Cat. No reference at all to this work. And I said, oh, did you like forget? Did you not know about that? And he said, well, we knew about it, but I didn't want to have to bother going in and adding a reference. Yeah, right. You have a prediction that these people had a nature com, supposedly verified it experimentally, and you're just not going to bother putting it in? They knew damn well it was wrong. They didn't want to make reference of it. But he said, that's true, you can't. Maybe you can devise the experiment some other way and get rid of that. I don't know, he said, but don't quote me on this. Because they're all buddies in the community. They're all offspring of Ronoffs. I guess they don't want to. But that's it. Thank you.
I don't know if there's another class in here, but we better wrap it up.